Just more Oxford College here, physics. Oxford College physics. Anyways, let's just get started, shall we? Yeah, we shall. So what we want to do at this point is continue on with analyzing systems regarding forces acting, accelerations produced, and all sorts of scenarios. So we introduce another system. And it's a fun system. I am a big fan of this system just because, hey, I like it. I like it. So what is that system, you may ask, that I am a fan of? It is a system that involves this. Not a T, but whoa. Not gonna fall and hit me in the head? Great. This right here, what do you want to call this? I'm gonna call it an inclined plane, because that's what we call it. It's a plane, planar surface that's inclined relative to the horizontal by some angle here, which we can determine, but the only thing we're really mainly concerned with is, hey, it's an inclined plane. All right, so what do we want to do with an inclined plane? Well, what we want to really do is analyze the behavior of an object that is placed on an inclined plane. So what happens if I take this little mass here and I put it up on this inclined plane and then I let go of it? So right now the net force on it is equal to 0 because I'm pushing it up with my thumb, and that's something that's probably pulling it down. We'll get to that though, right? So what happens when I let go? You say, oh, it's going to slide down, and you are correct. It went from an initial velocity of 0 and slid down, increasing its velocity as it goes down the incline, accelerating down the incline. And I can produce greater accelerations, or I can produce smaller accelerations. I'd have to remove this. This isn't too difficult. Produce smaller accelerations like this. They're all contingent upon the inclination of this incline itself, what the angle of inclination is. So ultimately, this is what we want to start looking at: the inclined plane and how an object placed upon an inclined plane acts. So here's the first question for you. What must be responsible for the object going down the incline, right? What's responsible for the acceleration down the incline? I let go of it, there it goes. Well, the incline itself is exerting a normal force on the object, right? Let's think about that normal force really quick. So this object is pressing against the surface this way, and the surface responds by producing a normal force perpendicular to the surface, which would be this way, right? Perpendicular to the surface. Well, a force perpendicular to the surface can't be producing an acceleration in that direction, right? That doesn't make sense. I can't push on something that way and think that that's going to make it go up. That doesn't make any sense. So the normal force, though we can definitely see it's in contact with this, can't be responsible for it sliding down the incline. The normal force is perpendicular to the incline, the direction that's going to be accelerating. So what's left? That's right, the force of gravity. The force of gravity has to be responsible for it going down the incline. So what about that force of gravity? The true direction of the force of gravity is negative j hat, straight down, right? Well, the object can't just fall through the incline because the incline's there constraining the object to its surface. So we have to kind of start thinking about, well, components of the gravitational force. There has to be some amount of the gravitational force that we can say is directed down the incline, which is responsible for that acceleration down the incline in this particular case. That's what we want to do. We want to start modeling the system of an inclined plane, seeing what's pertinent, and extracting out the ability to understand the behavior of an object placed on an inclined plane. So go ahead and put this inclined plane, decline the inclined plane, if you will. And we will start taking a look. All right, so inclined plane, like an airplane, just a planar surface. So let's draw this out. I can draw a nice little inclined plane. This is sort of a wedge. We can have some theta sub I, which we'll call the angle of inclination. That is the angle that the incline makes relative to the horizontal. So that's a nice, easy thing. And then what do we want to do? We want to put an object on this incline. So let's take a blue object, shall we? And let's just put it on this. Say, hey, this blue object has some mass m. And what we want to do is say what forces are acting on this object. Now, at this point right now, we haven't discussed forces of friction, and we're not going to yet. So we're going to ignore any friction forces that are possibly in the mix and just focus on, well, two familiar forces that we've already dealt with. One being the normal force, the second being the gravitational force. Those two forces, we're going to say, are the only forces acting on this object. And what we're going to do is kind of start to analyze the system. So, in this particular case, we will assume that only the normal force and the force due to gravity are acting on the mass. Oh, messy but that's how it goes sometimes. So if that is the case, let us go ahead and draw those forces in, right? Well, the normal force, once again, is perpendicular to the surface regarding the point of contact. Well, that just means that the normal force has to be like this. We've got ourselves n hat. We can draw a little square there to show, hey, that's a right angle with respect to the surface. All right, there's our normal force. Well, what else do we have? It could be a little straighter, huh? Ooh, is that going to bug me? That's okay. If we've got another force that would be, that's not going to work out. We've got ourselves another force that would be straight down like this. Which one is this going to be? Right, this is going to be the force due to gravity. Force due to gravity is negative mgj hat. There's no reason it still shouldn't be. That's it. So here's the two forces acting. One of them completely perpendicular to the surface of the plane, and one of them is just straight down. Well, what do we have? Well, first off, these two forces aren't along the same direction, or aren't along the same dimension, we should say. They are in different directions, right? Well, how are we going to approach this then? What direction is this object going to accelerate? You say, well, it's going to accelerate down the incline, right? Because, as we said, a component of gravity must be directed down the incline that's producing that acceleration. So what we're going to do here is not think about things in terms of I hat and j hat components, because it turns out not to be super convenient. We'll get to that. But we're going to think about things in terms of components that are parallel to the incline and perpendicular to the incline. Why? Because all of the motion is going to be constrained to be parallel to the incline, which really one-dimensionalizes things. If we want to treat it in terms of I hat and j hat components, well, this object under its acceleration due to gravity would be accelerating that way and would be accelerating that way, and have both I hat and j hat components of acceleration. It's easiest just to say, hey, it's accelerating down the incline, let that be the direction of the acceleration, and just deal with one dimension of acceleration. So, let us resolve the force due to gravity into components. That are parallel and perpendicular. to the plane of the incline. So any vector can always be resolved into two mutually perpendicular vectors with respect to something. What we've been doing is taking a given vector and resolving it into two mutually perpendicular vectors that lie along the I hat and j hat dimensions. But really we could do it with respect to anything. Always break up a vector into two separate components with respect to something else. That's exactly what we're going to do. So what I want to note is this vector here can be broken up into two perpendicular parts. One part that is parallel to the incline, and one part that is perpendicular to the incline. So let's start with the perpendicular component. I just need to form this. This, and then we've got this. I'm going to call this right here FG with an upside down T. That's FG perpendicular hat. I'm going to call this right here FG with two lines. Means parallel hat. And these two vectors here are perpendicular to one another. So really we're just breaking this vector up into two components, parallel and perpendicular. So let's write those down. FG upside down T, we're just going to call it FG perpendicular hat, is the perpendicular component of F hat sub G, and FG parallel hat is parallel component of F sub G relative to the incline. So we've got a parallel and perpendicular. All right, what we want to be able to do is figure out how to resolve this F sub G into its parallel and perpendicular components. Parallel and perpendicular. So what we got to be able to do is find some way that they're related to one another. So F sub G is easy, right? That's just mg. How do we get the perpendicular and parallel components of it? Well, that's a good question. Well, let us proceed. So, I'm going to redraw this really quick. Say, let's find FG perpendicular hat and FG parallel hat. So let me take this. And I'm just going to focus on those particular vectors here. We've got FG itself is a vector that goes like this. But then I'm just going to kind of draw this straight down so we can see that we can make another triangle out of this. So this is F sub G. Then we've also got ourselves this perpendicular to the surface itself. FG perpendicular. And then we've got this, which is FG parallel. And with that, again, that is a nice right angle between FG parallel, oops, it's perpendicular, sorry, FG perpendicular and FG parallel. And what do we have? We can start writing in some angles here. First off, the angle of the incline we'll call, again, theta sub I, just like we had up there. Well, let's call this angle right here, I'm going to call that phi, just for right now, call it something. Because if we can figure out what phi is, then we can take this right triangle and figure out how FG perpendicular and FG parallel are related to F sub G by this phi, via some trigonometric identities, right? So, let us go ahead and write something out really quick. If you take this triangle here, and what we'll do is we'll just kind of rotate it so that this is the base on the ground, just so we can see things better. I can take this triangle and draw it like this. I'm going to expand it out a little bit. So that would be there. That would be there. And this would be there. That's our F sub G. This would be like our FG parallel, FG perpendicular, and this would be our angle phi. I can make, again, trigonometric relations between those four quantities here. Well, if I start looking at, say, the cosine of phi. Cosine of phi is adjacent over hypotenuse, right? Cosine of phi is equal to adjacent over hypotenuse, which gives us FG perpendicular divided by F sub G. FG perpendicular divided by F sub G. Well, what does that give us the ability to say? Give us the ability to say that FG perpendicular is FG times the cosine of phi. There's the perpendicular component of the gravitational force relative to the incline is the magnitude of the gravitational force multiplied by the cosine of that angle phi right there. All right, that's good. We can also do the sine of phi. Well, the sine of phi is defined by opposite over hypotenuse. So the sine of phi is going to be FG parallel divided by F sub G. Let's do it how I wrote it in the first time. Do opposite over hypotenuse, which is going to be FG parallel divided by F sub G, which we can then solve that out for FG parallel and get that FG parallel is equal to FG times the sine of a phi. So what do we have? We have the ability to find the parallel and perpendicular components of the gravitational force in terms of the true gravitational force, mg, or F sub g, times the sine and cosine of the angle that F sub g perpendicular makes with respect to F sub g. So again, this triangle is this one, rotated, and then I made it a little bit bigger so we can see it. So we need to be able to determine what is that phi then, right? What is phi? How is that related to other things? Well, let us see if we can find phi. So let's do this. I've extended this down because it just forms a straight line, right? So we've got that would be a 90-degree angle, the direction of the true gravitational force and the base of this incline. All right, so there's another angle that we can go ahead and define. Let's define this angle right there. I'm just going to call that gamma. It's a little upside down fish or a 90-degree rotated alpha. Just naming it something. So how many degrees are in a triangle? That's right, 180. So we've got ourselves this triangle right here. This nice right triangle, which has theta sub I plus 90 plus gamma. Those have to add up to be 180 degrees. So we can write that out. Theta sub I plus 90 degrees plus gamma is equal to 180 degrees. And we can go a little bit further with that, right? I can write this as theta sub I plus gamma then is equal to 90 degrees. That seems reasonable. These two angles have to add up to be 90 degrees. Good. All right. So what else can we do with this? Well, what else do we have here? This is the perpendicular component of the gravitational force right here, perpendicular to the incline. It must be making a 90-degree angle with respect to the incline itself, right? So if we think about what's entailed within this 90 degrees, hey, that has to be phi plus gamma. This right here says that phi plus gamma must be equal to 90 degrees. 90-degree angle, how's that plus that? All right, so this is what we've got. We've got that phi plus gamma must be equal to 90 degrees. We've also got that theta sub I plus gamma must be equal to 90 degrees. What does that tell us? Well, geometrically, it explicitly tells us that this angle phi is the same angle as this, the angle of inclination. So, phi is equal to theta sub I. What does that do for us? Well, it allows us to rewrite these in terms of something that is generally either measurable or given. The angle of inclination. So if we got this phi and this phi are really theta sub I. So from this, we get this. Fg perpendicular, the magnitude of the perpendicular component of the gravitational force is equal to, well, F sub g is mg, right? The magnitude. So we'll just write this as mg times the cosine of a theta sub I. And what else do we get? Well, this is just mg, and that's theta sub I as well. And we've got that Fg parallel is equal to mg times the sine of theta sub I. This is what we wanted to be able to get. Given that we know the mass and the angle of inclination, we can determine what the perpendicular and parallel components of the gravitational force are. And their directions are pretty easy because, well, it has to be downward. It's being pressed against the incline for the perpendicular component, which means that the normal force has to be up. And this one has to be directed down the incline at all times. The force of gravity parallel to the incline is down the incline. We don't want to use I hat and J hat because now we kind of one-dimensionalize things. We've broken it up into two things in which all the motions constrained to be parallel to the incline. There's no changes in motion perpendicular to the incline. If there were, that would mean that the object's either coming off of the incline or going through the incline, which would make it not an inclined plane problem anymore, which would be kind of senseless in a sense. So, these are really important because they will enable us to really easily discuss an inclined plane problem. So, mg cosine theta, mg sine theta, perpendicular, parallel components of the gravitational force are respectively. All right, so let us come back and look at some other things now. Come back to this scenario where, hey, we can figure out what the parallel and perpendicular components are, but there's the normal force in there too. So, what happens if we want to know what is the normal force acting on this object? And furthermore, what kind of acceleration do we get if we let go of the object? And those are the only forces acting. So now consider the normal force acting on the mass. We want to know what it is. Well, we can start again breaking things up into parallel and perpendicular components. Note, the net force perpendicular to the incline must be equal to 0 if it's going to stay on the incline. Why? Once again, if it weren't 0, we'd have an acceleration perpendicular to the incline, which means that the object would either accelerate that way or it'd accelerate that way, which means that it wouldn't be on the incline any longer. And this again is for an inclined plane where the angle isn't changing with time. We're not looking at that. This is a static incline here. So this, no changes in motion. Perpendicular to the incline. So that's important because what does that allow us to do? Well, for this particular case, where we've just got the gravitational force and the normal force acting, we have that the net force perpendicular to the incline is equal to 0. Net force produces nothing, no acceleration, and the net force, once again, perpendicular to the incline is equal to the vector sum of all forces acting perpendicular to the incline. Well, the forces that are acting perpendicular to the incline are n hat and fg perpendicular hat. So let me just note this. Net force perpendicular to the incline, just so we're sure what those quantities are referring to. Sigma F perpendicular. All right, so what does that give us? Well, net force perpendicular equals 0. Net force perpendicular is the sum of the two forces that are perpendicular, which then gives us that n hat plus fg perpendicular hat must be equal to 0, which then gives us that n hat is equal to negative fg perpendicular hat. What does that say? It says that the normal force acting on this mass is equal in magnitude but opposite in direction with respect to the perpendicular component of the gravitational force. So this is where you run into a little bit of, not trouble, but something you got to be careful of, and that's signs of things. Again, signs regarding vectors are always directional. This means opposite of. Opposite of what? Opposite of the direction of this in this case. What is the direction? Well, we're not using a standardized I hat and J hat, so we can't say positive I hat, negative I hat, positive J hat, negative J hat. When we rotate into the frame of this incline, what we need to be able to interpret is what the direction is, perpendicular up versus perpendicular down. That's fine. We have a sign convention that we can utilize. We can say plus perpendicular is perpendicular up, minus means perpendicular down. For the perpendicular component, it really doesn't end up mattering that much because the net force is going to be equal to 0. For the parallel components, that's where we got to be a little bit more careful. But ultimately, what do we get with this? We get equal magnitudes. Opposite directions. We'll come over here. That means that the magnitude of n hat is equal to the magnitude of fg perpendicular hat, which is then equal to mg times the cosine of theta sub I. There is the magnitude of the normal force, the amount of force that the surface must produce on the object to keep the object constrained to the surface. It's not just mg, it's mg times the cosine of the angle of inclination. Take a look at that momentarily. What else do we have? Well, we have that they're in opposite directions. One's perpendicular up, one's perpendicular down. The main thing is we can get the magnitude of it. All right, so let's think about this. Let me take this object here. I'll just hold on to this. And I'll say that this is held completely level. If this is completely level, the angle of inclination would be, that's right, it would be 0. And if we were to then compute what is the magnitude of the normal force acting, it would be mg times the cosine of 0. What is the cosine of 0? That's right, it's just 1. So the normal force acting in this case would be mg. That's it. We already know that. Gravity's pushing it down, pulling it down. The normal force pushes it back up with the same amount of force, mg. Well, let's take this scenario. What happens if I go ahead, hit the ceiling? Yep, too much. What happens if I go like this? If I take this and say, now this is a 90-degree angle. I take the object and I hold it against, but then I let go. What's the normal force acting as it goes down? Well, it's not being pushed against the surface by gravity anymore. What about the parallel direction? Well, I'm going to redraw that a little bit just so that we can see with respect to the mass. We've got this mass there. That's a great. And what do we have? Well, we've got ourselves, now I'm going to break up the force of gravity into its components. We've got the normal force, n hat. We've got the perpendicular component of the gravitational force, Fg perpendicular hat. And instead of drawing the parallel component down here, I'm going to draw it up here because it's really acting on the mass, right? So there it was drawn so that we could form the triangle so that we could extract out the relations. But now I'm just going to draw right here. There is Fg parallel hat, right there, the component of the gravity that's directed down the incline. Well, if we wanted to know, say, hey, what's the acceleration of this object? Is the overall acceleration of the mass if only F sub g hat and n hat act? Well, we've already gotten that the net force perpendicular to the incline has to be equal to 0. So, well, there is no motion perpendicular to the incline. That's kind of a... That makes me feel a little bit better. At any rate, what are we left with? Well, we're left with the net force parallel to the incline. We've got that the net force parallel to the incline produces the acceleration of the mass parallel to the incline, which doesn't have to be 0 like the perpendicular components. So this is what we get. Net force parallel to the incline produces the acceleration of the mass parallel to the incline. All right, well, there's what the net force, or what it produces. What is the net force? Well, in this case, if we've only got these two forces acting, the normal force and the perpendicular component of the gravitational force are both perpendicular forces. There's only one parallel force regarding the incline, and in this case, we then have the net force parallel to the incline is Fg parallel hat. So, net force produces, net force is composed of, and from there, we've got ourselves that MA parallel hat is equal to Fg parallel hat, which then gives us the ability to solve for A parallel. And we've got A parallel hat is equal to F sub G parallel hat divided by M. And what do we know? M can only be positive, right? There's no negative mass that's been found at this point in time. It's something that you release and it goes up instead of down due to gravity. Not yet, anyway. So what do we have here? Well, the acceleration has to be in the same direction as the gravitational force directed down the incline. So we already know the direction. So we have some sign that correlates that. We could call that the positive direction or the negative direction. Because again, this ends up being one-dimensional acceleration parallel to the incline. So moreover, with this being the only thing that we have in terms of the force acting, we can write that the magnitude of the acceleration is equal to the magnitude of the parallel component of the gravitational force divided by m, which is then mg times the sine of theta sub I. There's the magnitude of the gravitational force parallel to the incline divided by m, which then gives us that the magnitude of A parallel is equal to g times the sine theta sub I, where g is just 9.8 meters per second squared, and theta is the angle of inclination somewhere between 0 and 90 degrees. The direction is down the incline in the direction of the parallel component of the gravitational force. So let's take a look at this now. I take, I'm gonna break, make sure it doesn't hit my toe. I take a mass here. We've got ourselves 1 kilogram of mass. I take it, I put it on the incline, and I release it from rest, and right now the angle of inclination is 0. What is the acceleration of this mass? So well, it's not moving, not changing its motion, the acceleration looks like it should be 0, right? And then we come over here and say, well, what happens if we put in 0 degrees for theta sub I? That's right, we get 0, right? Sine of 0 is 0, so the acceleration parallel to the incline is 0. Whereas, what happens if I go like this? I put this at 90 degrees, and I take this mass, I hold it against the incline, then I release it from rest. What was the acceleration of that mass? Well, it's like it was in free fall, right? It was in free fall. Straight down. The acceleration was g. What happens if you put in 90 degrees right here? The angle of inclination. Well, the sine of 90 is 1. And then we get the acceleration, the magnitude of the acceleration is just g. Anywhere in between there, we get variation of the acceleration in between g and 0, depending on the angle of inclination. As the angle gets steeper and steeper and steeper, the acceleration down the incline due to gravity gets larger and larger and larger, approaching its maximum value. Again, this is assuming that only the gravitational force and the normal force are acting on the object. Start throwing in other forces, then you change the system. But this is how we wanted to start off. Just looking at this. All right, so inclines, good stuff. We're going to do quite a bit with inclines, so we'll be doing a few problems to investigate some aspects of them, throw in some applied forces, have something sliding up the incline, being pushed up, pulled up, whatever you want, pulled down, all sorts of things that you can do. Eventually we add in some other stuff like friction and all sorts of good stuff. But that's it for now for the inclines. The main point was being able to get what the parallel and perpendicular components of the gravitational force were and being able to utilize them. That's that. All right? All right. Have a good one.